Any questions about last time? Okay. Okay, so we're wrapping up this part of the course when we introduce the rules of logic and the rules of sets, algebra of sets and algebra of logic, and we can use them. We could use them. We will continue to learn them and how to use them in practice rather than just stating them as a list of formulas. We're going to be using them a lot, sometimes implicitly, sometimes explicitly, but we are mostly done with that. So, and we'll try to deal with proofs that are more complex than these, especially that one in the middle that I illustrated, the 2x plus 1 is equal to 3. I used it as an illustration of if and only if proof, which is the proof of the theorem that is right below. Which is one line proof. So just for practice, that kind of proof is possible, even though not necessarily typical. So what I'm talking about then, proving the original theorem, the equations that sometimes you solve equations in that manner, and that is typical. Once again, I'm talking about this part. Okay, so 2x plus 1 is equal to 3. You transform the equation into simpler and simpler equation, and then at the end you arrive to the answer. Okay, so well, actually this one is as well. Both of these are valid ways of solving an equation in pretty much one line. There, so it's more complicated, and the string of those if and only if arrows could be very long. But generally, it works out fine. Okay, when it is anything else, I'll prove some more less algebraic. Then maybe not. You have to do it both ways separately. So that is the. But sometimes it works out if it's simple enough, such as the statement at the top. So x is divisible by 6 if and only if x is divisible by 2 and by 3. Okay, so you could try to write it in one line if you just careful enough. So, for example, let me just outline what it might look like. Let me start with it. So, x divisible by 6, if and only if x is divisible by 3, and x is divisible by 2. Okay, so you can certainly go from one way to the other and back. So x is divisible by 6. X is equal to 6n. Okay, and this is x is equal to 3m. X is equal to 2n. Okay, so these are the definitions of these statements. In fact, I could connect. So I know what I want to prove. I want to prove this, but your analysis, as you transition from one statement to the next, which we did, once again you can connect the new statements to the old one once again with those signs. So this is, because it is the definition, then whatever we statement in words, divisibility, in terms of divisibility, is translated into a statement, algebraic statement, and these are equivalent statements. So all of these are equivalent statements, even though I did not write them completely. So there is an n, there is an m, there is a k. Okay. So that would be the three statements that I have here in mind. I translated them with the language of with the definitions that we know into these statements, and now that is how I wanna continue. And so I'm one step closer to proving it, because, well, words might not be useful. The words, definitions are not always translated into with the definitions to something where the definition came from. It's not always the case, because otherwise, what's the point of the definition? Just say 6n, that's divisible by, why even use words? It is when you have theorems. You might be referring to theorems that we're going to do today. then maybe you might not need to unwrap the definition. So when it is as simple as that, you probably should. But sometimes, for example, you're referring to right triangle, then you don't really have to tell what right triangle is if your theory that you're using already uses the word right triangle. So if you say right triangle, now I'm using the Pythagorean theorem, which is about right triangles, and just go on, keep going. Okay, so you don't have to explain what right triangle is. Okay, so but this one is probably okay. So so how do you prove it? So how do we make this connection?
Isn't and intended to be multiplication though?
With what part?
So we say 6n needs to equal 3n times 2k.
Right. Okay. And then what?
And you just show that 6n is equivalent to 3n times 2k.
Right. So I think what you're saying is you want to factor 6. You factor 6 first. So you can say x is equal to, in fact, 3 times 2n, right? Okay? And then you can point out what you need to find m and k. So what is m? This is given, right? What?
X divided by 3.
It is, but specifically, you can be more specific. X divided by 3, you can be more specific now. Look at that line on the left. X divided by 3 is what?
6n divided by 3.
Yes, 6. I already have factored it, so I certainly don't need to factor it in once you have the idea, but that little thing is actually does give you an idea of what we're trying to accomplish and where this referring to came from. It came from factorization of 6. Okay, so and then you just go on as was suggested. M is equal to x over 3, which happens to be 2n. Remember, we're supposed to demonstrate that there is an m, which is an integer. Okay, so I skipped that, but m is an integer. So if you just write x over 3, that wouldn't do it. But if we already have factorization of x over there, and I'm through the computation discovered that x is equal to n, then I know that this is an integer. Why? Because we started with n an integer, and then we ended with m equal to 2n. We know it's also an integer. Okay, so that proves the first part, and then the same with the second. I have what is k. K is x over 2, which means it is 3n. Once again, an integer, because n is an integer. Okay, so what have we accomplished now? But does this part? I intentionally didn't include. I know I'm asking you to. What have we accomplished? What is has been proven by this analysis? Because the first two lines we just restate the theory that we want to prove, but now what is the? And we did some analysis. What does the analysis prove to us? Well, we need to go left, right. Is it from left to right, from right to left, or both? Is it both? No, it's only one.
We have to go right because the f and only f.
You're going. We need to go both left and right, but that proves the what we're supposed to prove equivalency. But what have we proven so far in this? What I put in the circle, we proved it only one way. We started with x is divisible by 6, so x is equal to 3 times 2 times n, and then we found We found m and we found k, and we demonstrated they are integers. Okay, so that proves half of the theorem, right? So from left to right, if it is divisible by 6, then it is divisible by 3, and it is divisible by 2. Okay, so that does not prove, as stated, does not prove that that the vice versa is also true. Okay, so you have to actually start over. Okay, so just try to think that way. So we were starting with it. So always that's why it's better to do it separately. The two proofs, two arrows, two proofs. It's easy to do all of them separately, unlike that algebraic equation I showed you just a minute ago. It is better to do one at a time. If there is any possibility of confusion, start with one. Say, this is what I know. So this is known. Okay, so this is known. X is divisible by 6. X is equal to 6 times n for some integer n. That's what we know. And then you make conclusions. And then you see if those conclusions match what you're supposed to prove. They did, but it's only one way. So let's do the other way. So what do we do to go the other way? So once again, set your mind and make it clear what is given. So what is given is we don't have to demonstrate that it's an integer anymore. So there is m, integer. So I'm rewriting it, but with a different idea in mind. So this is what's given, and this is also given. Two things are given. There's a k, also an integer, so that x is equal to 2k. And then we're supposed to demonstrate the existence of what? Of n. So usually just say find n. Remember, find n such that integer, naturally, x is equal to 6n. Okay, so that's what we have demonstrated, right? We actually pointed out in the left part. We pointed out what m and n are, m and k are. Okay, in terms of n. Okay, that's helped us. The assumption that n was an integer proved that m and k were integers too. So we are going in the opposite direction. So this time we have two integers, m and k. We want to demonstrate. We want to find what n is. So what is n? Yeah, okay, x divided by 6. X divided by 6. Yeah, I'm sorry, n divided. N is equal to x divided by 6. Okay, which is fine. We know it is. I mean, we were looking for x for n satisfying this equation, so it has to be equal to 6 over 6. How do we demonstrate that it's an integer? What?
The right side is made up of integers?
It is made up. Okay. So let's investigate that. So x is equal to 3m. So let's see. So n will be based on the first half on the right. X is equal to 3m. So it's x over 6 becomes 3m over 6. Okay. And secondly, n is also equal to 2k over 6. Okay. We just substitute. Okay, and so it helps a little. It helps a little, right? I can cancel 3, so I have m over 2, and I have also k over 3. Okay, so this does not prove that n is an integer. Right, so because m is an integer, k is an integer, yes, but m over 2, how do we know that it is an integer?
We're given that n is an integer.
What?
We're given that n is an integer.
Yes, but m over 2 is not given as an integer. We're trying to demonstrate that n is an integer. Let's demonstrate that n is an integer. Okay, and we don't have it. It worked out the other way. You see how nicely it worked out. We just took our x over 3, and we have suddenly 2 over n right there. 2 over n, and it is It was an integer, right? So when you multiply an integer by an integer, you have an integer. Okay. So, but now we divide. So it is possible that m over 2 is not an integer. Okay. So how do we sort it out? The thing is we have two of them. So two. If we only had one and not the other, well, we're stuck. Then we would be wrong. But we have both of them. So maybe there is something that is useful here. Well, I mean maybe dividing is actually premature. Maybe we are actually better off looking at these. Okay, so that's the same x, and we know that x is an integer. So it is actually turns out to be, if I go that way, that's I have something else. What do I have? I have x is equal to 3m, and it is equal to 2k. M and k are integers. So if you forget about x, what does this tell you? If 3m is equal to 2k, what can you say about, say, m?
M is equal to 2k divided by 3.
Okay. Anything more relevant? What kind of number is m? So once again, 3m is equal to 2k. What kind of number is m?
An integer?
Oh, it definitely is an integer. They all are, but more so. Compare the. Do you see the 2 on the right? What? It is an even. It is an even number. That's right. So m is in fact even. So once again, we have on the right we have 2k on the right, which makes this whole thing even, right? So in other words, 3m is an even number. That can 3 make this number even? No, it cannot. You need m to be even in order to 3m to be even. Okay, so we conclude then indeed, because 2k is even, therefore m is even, and so 2k is even, m is even, and why do I want that? Why does it matter?
Because then m over 2 is an integer.
That's right, so then m over 2 is an integer. Okay, so that's how it works out, and then you do the same with the other, with k, so it's slightly more complicated because you can speak of even, but you can see that 3m is divisible by 3, which makes k divisible by 3. And so once again, you conclude that k over 3 is an integer. Okay? So this is kind of informal comparison, and it certainly is plausible, but if you want to be strict, there is a theorem that at this point you invoke, and that theorem is the fundamental theorem of arithmetic. I'm not sure if you heard of it, probably may have in pre-calculus. It's about factorization of integers. What do we know about factorizations of integers? So they can be factorized into integers in a unique manner. Okay, so every integer can be represented as the product of primes. Remember this? In a manner unique up to an order, or the order of the factors after their order. Okay, so very helpful theorem. We might prove at some point. But, as an example, say 100 is equal to 50 times 2 is equal to 25 times 2 times 2 is equal to 5 times 5 times 2 times 2. So these are the prime factors, right? And there will be the same no matter how you may try to do factorization in different order. The end result will be the same. Just the 2 and 5 might be rearranged in a different order, but the result is the same. So that's why if you want to have a very specific reference to in order to support our argument right there, that's the way to go. So 3m is equal to 2k. So once again, think about it as 2k.
Can you read the theorem?
Every integer can be represented as the product of primes in a manner unique up to their order. Okay, so that is are you familiar with the fundamental theorem of algebra about factorization of polynomials? Factoring polynomials from pre-calculus. Remember that one? So the idea is the same, that you can and that's where long division comes from. But let's not go there. So this is a fairly intuitive theorem that indeed such a factorization is possible to begin with, and then it's also not very hard to make an argument that there cannot be two different factorization, because once you start canceling, then you have divisible by 3 on the left and not divisible by 3 on the right. So if you have 3 on the left, you got have 3 on the right. Okay. So we are certainly not right in the position to do this proof altogether, but at least we've seen examples of when it works out, and this is the example of why an example of why fundamental theorem should hold. So once again, if you have 3 on the left, then you have to have 3 somewhere on the right, and that's why k has to be divisible by 3. Okay. On the other hand, since we have 2 on the right, there must be 2 somewhere on the left. These are 2 equal integers, and so they have identical factorizations. So same parameterization on the left and on the right. So which means that if there's a 2 on the right, you have 2 on the left somewhere where inside of M. Okay, so that's what the argument we just did right there before we got to this theorem. So it's a convenient theorem, but we're going to use it a few times. We have used it. It's impossible to do any kind of divisibility discussion without the fundamental theorem. Okay, so and then that is worthwhile proving when we're a little bit more comfortable with longer proofs. But we will be doing it little by little. Okay, so let's step away from divisibility, and divisibility, which we have discussed. We used as a primary example for everything we talked about, and do something slightly more substantial. And the proofs will become more challenging, obviously, from this a little bit. And one that I want to talk about is the this familiar result. I hope it is familiar. Square root of 2 is irrational. So, you've heard of this? Irrational meaning an irrational number, right? You've heard of it. Okay, so let's prove it. Well, before we prove it, certainly the importance of this result, for the result goes way more than 2,000 years. And if you don't recall the story, the ancient Greeks thought of everything to be about rational numbers. And not just mathematics, the whole world was made of integers. Integers make up rational numbers, and then everything is about rational numbers. And then with the discovery that the diagonal by the Pythagorean theorem, then pretty much the diagonal of a 1 by 1 square is square root of 2. And then it was demonstrated that there was a proof, one of very early non-geometric proofs, and they demonstrated that the number was irrational. It was a big crisis in our religion. Okay, so it was like a religion for them. They were actually called the Pythagoreans. Anyway, so the story goes that they forced the person to commit suicide when he proved this. But, see, so it was a serious matter. So we just retrace this a little bit. Yeah, and they couldn't do anything about the proof. They dealt with the person rather than with the proof. Because that's mathematics. It's hard to do anything once it's on paper and it's right there. So find a flaw if you could. Okay, so let's do it. Let's do it. Square root of 2 is irrational. So as always, when we're facing a statement that we typically write in words, as I did, but I could have even make it even less algebraic by saying that as I did, the diagonal of 1 by 1 square is irrational. So like that. Okay, but since we are here, we will be expanding this statement little by little on through actually step number 1, the definitions, right? Unless you already have a theorem in mind. Okay, so if you have a theorem about irrational numbers, then you might not deal with the definitions. So definitions or theorems. So we might still need theorems, but you never know. So you just as well write the definitions. So I certainly don't have another theorem about irrational numbers in mind. So it is one of those early theorems that you prove, and then this is actually something to make reference to. And some of the theorems are so fundamental that they're actually ones they don't use other theorems. Okay, so that's the one. So that it means that you're going to need definitions. Okay, and then once you did it, you don't have to maybe. So anyway, the definition of irrationality to begin with. So let me first state it this way, slightly more logical. X is equal to square root of 2, then X is irrational. Irrational. Okay? Okay, so we have to then state the definition of irrational. So, what's the definition of irrational? Not rational, that's fine. Okay, then you have to do another definition then, and say what rational is. What's rational number?
I wouldn't say not irrational, but that doesn't
No, you can keep going.
Yeah, right.
So what's the definition of a rational number?
Terminating?
What?
Terminating?
No, 1/3 is a rational number. It does not terminate. The vice versa is true, as a matter of fact. So that's an example of a statement that the converse is not true. So if a terminating decimal is rational, but not necessarily every rational is terminating. Okay.
Is that what you're saying? If a number terminates, it's rational, but you can't say
if it's rational, then it terminates.
Yeah,
Right.
okay, yeah.
So once again, 1/3 is a rational number, but it does not terminate. So that's a counterexample. Okay. So remember this. So it's not the same. We demonstrated, we showed that there is an exception, and that's all it takes. Terminating, and then
0.3 repeating is still finite? Or is that
no, 0.33 dot means that it's not terminating. It keeps going with threes, so it's not terminating, so it's an infinite decimal. Okay, so rational. Nobody. What about rational functions? I mean, you did calculus. What is rational function? Rational function. Okay, so the word ratio mean anything to you? Ratio. That's the definition of rational numbers. It is a ratio. Of what? Irrational number is a ratio of integers, of two integers. Okay, so then once I have this ratio, meaning for fraction, okay, so I could just write x is not equal to p over q, q integers, q not equal to 0. Okay, so that's the definition, and now the word irrational is all irrational is gone, and I have my my statement right there. Okay, so then at that point you could just write it x is equal to the square root of 2. So I'm not doing anything here. So what I'm saying is that square root of x is not equal to p over q, where p and q are integers, and square root of 2. Yeah, I don't know this anyway. Let me start over here. X is equal to square root of 2. I want to demonstrate that x is not equal to p over q, p and q are integers, q is not equal to 0. Okay, so that is one of those proofs that are proving the negative, right? So how do you prove it, practically speaking? You have a specific number on the left. So you think then on the right you'd be doing something specific, but not so, because now you have to verify that no matter for what pair of integers p and q you pick, it's not equal. That's a lot of work, and so you have infinitely many integers. So what do we do instead? How do we prove negatives? What? So let me, since we are talking about the, let me maybe stay away from algebra for the time being, and then x is not a ratio of two integers, then let me put it this way, not, remember this, negation, okay, so and then we are in this, so I'm just repeating this. Okay, so not true that x is equal to p and q are integers. Okay, the idea of when you prove a negative, sometimes it doesn't necessarily be the case, but this is one of those cases when you have so much complexity on the right and you seemingly have something very simple on the left, you do go contrapositive. So this is what you want to prove from left to right. So let's try a statement that is equivalent but contrapositive.
You need to show that p over q is not equal to two. And
that's right, yeah.
And that big symbol of the parentheses.
It's we use the bar above it, but when the statement is so long, it is just more convenient to put this kind of gallows symbol in front of the statement. So it's the same as putting a bar above it.
Okay.
So it's negation. Okay. So contrapositive means that, remember, I reverse the arrow. Well, I still put question mark here. And then I negate the two statements. So that gallows symbol goes away. I still have p over q, pq integers, q not equal to 0. And then what I'm concluding that x is not equal to square root of 2. That's the negation, right? Okay, so this kind of proof actually has a special name. It's called proof by contradiction. That's what contrapositive is. We assume the opposite of what we have, and then we arrive to a contradiction to the condition of the original theorem. So the condition, the hypothesis of the original condition was x is equal to square root of 2. And if how do we prove that our theorem? Then we assume that our conclusion is wrong, and then demonstrate that it contradicts our assumption. That's what this is, right? So we need to demonstrate that if x, we started with a more complex thing, x is equal to square root of p over q, then we want to show that x cannot possibly be equal to square root of 2. Okay, so that's a proof by contradiction, meaning, so let me write it out. So assume that x is equal to p over q, and demonstrate, well, I think we can simplify it slightly here. Square root of 2 is equal to p over q. Demonstrate that this is impossible. Well, one way, let's, before we actually get to the proof, let's just connect it back to things we have done. What is the interpretation of this in terms of sets? Well, if we go, let's just forget about this. This is the conclusion. This is the theorem, right, at the top. X is equal to square root of 2, then x is equal to, is irrational. Then let's just, for exercise, what is the interpretation of the statement in terms of sets? No, remember the implication is translated as inclusion, right? So, like this. You just have to say what those sets are. And one is a very simple set, right? It's the square root of 2. Okay, so in other words, so square root of 2 belongs to, I don't have the inclusion anymore because there's only one element. I'll put it this way. Irrational numbers. Right? So that's how you can restate it in terms of sets. So sets or elements of sets. So square root of 2 belongs to the set of irrational numbers. So then everything what we have done here also can be restated in terms of sets. So do you see what, well, let's continue on and just, okay, let me just rewrite it. Square root of 2 is not rational. Square root of 2 does not belong to, this is familiar with this notation, q for rational numbers. So square root of 2 does not belong to rational numbers. That's another way to, another one that we want to prove. Okay, but now the contrapositive is slightly trickier, but let's just skip over and just let's concentrate on the word impossible. What in terms of sets, what does impossible mean? The empty set. The emptiness of a certain set is empty. That's what impossible means. So I just write what that set is, and what varies. Square root of 2 is not a set anymore, but p and q will vary, 2 integers. So this is how I can write it. I write, just square root of 2 is equal to p over q, pq integers is empty. Okay. So I take pairs of integers, all possible pairs of integers, divide them, and see if any of this infinity of fractions produce square root of 2. And the answer is no. So that set of those p's and q's is empty. Okay, so that's the idea behind the contradiction. You don't have to, once again, to make that translation, but just keep in mind that there's always a possibility. Okay, so we'll just stick to algebra and not sets. It's not always necessary. So we'll just follow this plan. So we assume that square root of 2 is equal to p and q, and show that it's impossible. Is another way to impossible is to demonstrate a contradiction with the facts that are known. Okay. So let's start over. So square root of 2 is equal to p over q. P, q are integers. Okay, and so q not equal to 0. And let's see what we can do about it. Okay, so the plan is here. So there must be a contradiction. We have to take a really good look at, or not literally a look, but rather algebraic look at this formula and see what we can do with it. So what do we do with it?
Well, I would just take numbers between a set interval and just plug them in and see if you can get square root of 2.
Really? Infinitely many?
No, for the set interval, because we know the square root of 2 is not between the square root of 1 and the square root of 4, and we know the square root of 4 is 2, and the square root of 1 is 1, so it's between 1 and 2.
Yeah, but P and Q could be very large.
Yes, but they would reduce down to numbers between 1 and 2.
Not necessarily.
No?
Say 999 divided by 1,000, and you can have as many 9s and 0s as you like, and there won't be any cancellation. The idea is more straightforward. You just square it. I mean, what we have been doing is we're all integers, and here we have a square root of 2, which is in the way. We know that P and Q are integers, so we're fine. But square root of 2 is not an irrational number, maybe. It's not an integer, so let's just square, and then we'll be in a much better place. Okay, so we're just shaking the tree and see if something kind of falls down. So far so good, right? So once again, if you want to be sure that what's going on every step that you make that you can retrace, you're not losing any information, then you just use that symbol. Okay, so I want to use this symbol one more time. What do I do? Get rid of the fraction once again. So I still have on the right a fraction. I don't want a fraction. I want integers only. Okay, so at this point, so why I was justified getting rid of the denominator because q is not equal to 0. So I just simply multiply by q squared and have a new equation of integers. I have integer on the left. I have integer on the right. And okay, so let's take a look at it. Any thoughts about it? We had discussed something just earlier today, something like that. Well, at this point, you can actually try to plug in a few values and then see what happens.
Is P even?
That's right. So you would conclude then, can you justify it? Why is P even?
Because it's 2 times an integer. And 2 times an integer is even.
Because 2q squared is even. Well, let's do it this way. Well, let's do it in a step-by-step procedure. So we're writing proof anyway. So 2q squared is even. P squared then, which is the same number, is even. Squared. P is even. That's the logic, slightly more expanded logical links here. So 2q squared is even. Okay, there we see 2 right there, so it's divisible by 2. The p squared is the same exact number, so certainly it's not even. The last step remains a little bit needs a little bit of an explanation. So how do we justify the last statement? P squared is even, and then p is even. So this is I want to justify.
Any even number of squares that you can number times.
You were making that mistake that you shouldn't. You were assuming that p is even and show that p squared is even. Okay, that's fine, but that's not what we care about. Fix your argument.
Any odd number squared is odd?
That's right. That's right. So not even produces not even. So that we're proving the contrapositive, right?
I heard.
So odd times odd is squared is odd. So which means that you cannot have p squared even, but p is not even. Okay. So contrapositive. We're proving the contrapositive here in the right direction, going in the right direction. It is, you see, the issue here is only the challenge here is that we have to go in the opposite. We want to go from p squared to p, and we know it's easy to go from p to p squared. Okay, so because you just multiply, and then which means that we have to do it this way. We have to actually look at odd numbers rather than even numbers. Okay, that's fine, and certainly that is by the way is I don't think we did it. So anyway, it is a lemma. You know what a lemma is?
No.
It is a statement that you use in the proof of your theorem, which may or may not be proven elsewhere. And I don't think we did it, but we could have certainly, right? To prove that odd times odd is really not hard. But if you want to keep moving, you don't want to stop and just prove it now. You just know it's true. Well, put it aside, and then you prove it later, or somebody else will. Okay, so that's what we do. That's called a lemma. And that's how you proceed for proof of a theorem. You use as many lemmas as necessary, as long as you're sure that they are correct. You keep moving because ultimately you want to arrive to your conclusion as quickly as possible. So you sort of mapped your proof as quickly as possible, and then you deal with the details. So it's like zoom in, zoom out, zoom in, then zoom in. So we'll prove this lemma if necessary later on. But at this time it appears that our conclusion is that this is the conclusion why we care is good. And then we were, okay, so that's a very good progress, and we just came up, it might not even be clear why it is so important, but it's certainly right there facing us. Okay, so how do we continue on with this? P is even, so let's draw some conclusion. How about we use the definition? P is even. So P is even, P is equal to 2n. Substitute. 2q squared is equal to 2n squared. Okay. Let's do some algebra. 2q squared, so whenever I forget the symbol, well, so far so good. Well, maybe I don't want to put this. 2q squared is equal to 4n squared. Cancel 2. Q squared is equal to 2n squared. Okay. Then what? Q is even. By the same logic. By the same logic, meaning it is, once you repeat your logic, that is another useful lemma. It is a statement that you use repetitively. So this logic that we have used here, over here, you can also call it a lemma. So, and the lemma is p squared is, well, not this one, actually slightly smaller. This is the logic over here. This is, that you can, p squared is even, means that p is even. So it appears that we're using it again. Okay, so anyway, just think about it a little bit more. We'll continue this next time.